Hello, welcome to this week 6 lectures on linear systems theory. So, last week we had done lots of analysis about equilibrium points. We did not define properly the notion of stability, but several characteristics of those equilibrium points via the phase space gave us some information whether the trajectories around the equilibrium point were coming back to the origin or going away from the origin or the equilibrium. Today we will give a formal notion of stability. Of course, we will do mostly in the linear setting and in general in the time varying setting. Okay, I will start with the following unforced system. I will not talk of inputs as yet. From x dot equal to a of t, x t with a certain initial conditions, and x is in general coming an n dimensional vector. In the previous control course, you would remember stability or one way of verifying stability is to look at the poles of the system, and then you had several characterizations of the poles being to the left, to the right, on the imaginary axis, repeated on the imaginary axis, and so on. All this came from a bit of input output notion of stability, right, and the condition to verify or the way we derive the pole based condition to verify stability comes actually from what is called as the absolute integrability of the impulse function, of the impulse response of the transfer function. We will not revisit those things. If you are interested, you can just go back to one of my earlier lectures that's listed here, just to get a little warm up on the BIBO notion of stability, of what was the bounded input, bounded output notions of stability. I will not elaborate that, but here what we will essentially focus is on the state space stability, more related to the kind of solutions we computed for the system of linear equations starting from the concept of a state transition matrix. Okay, so for this class of systems, what we know is that the solution is, well, given by x of t is phi, which is the state transition matrix and an initial condition. What we also know is that x star is an equilibrium point of the system if it satisfies a x star equal to 0, and in most linear cases the origin x star, the 0 vector is an equilibrium. It is always, even if the A matrix is not invertible, say if it is of this form, still 0 is an equilibrium. There could at some point of time be, well, multiple equilibriums, say this is an equilibrium point, the origin, maybe somewhere this is also equilibrium point. So, the line joining these 2 points is also so any point between these 2 points or the straight line joining these 2 points will also be in the equilibrium. Okay, so you will have essentially an equilibrium subspace. That is what we talked about in one of those conditions in equilibrium in previous week's lectures. Okay, so fairly we will just generally denote the notion of equilibrium as x star, and mostly we will deal with the origin. Even if the origin is not the equilibrium, you can change the coordinates or shift the origin. Slightly different than the nonlinear case, because okay, there we possibly will not have an equilibrium subspace, but we will have say isolated equilibrium points, say equilibrium point here, equilibrium point here, here, and so on, and each say if maybe the phase space goes something like this, okay, it could go this way, right, this and this. So this is a stable equilibrium, these 2 equilibriums could be unstable, and so on. So we have what they also call as isolated equilibrium points, but for us we will just assume that or we know that origin is the equilibrium, and that will be the equilibrium of interest, but just to for notational purposes we will just call it generally as x star. Okay, so the first definition of stability. what does it mean? Again, I am looking at stability is always defined with respect to an equilibrium x star. So, an equilibrium x star of the system x dot is a t x, and I just for ease of notation I just drop the time argument for x, is stable if for all epsilon greater than 0 there exists a delta which is a function of this epsilon, such that if I take the norm. So, this is a solution, right, how the solution trajectory moves, phi t t 0 x 0 will give me the solution. The norm of this solution minus x star is less than 0 whenever x 0 minus x star is less than delta. Okay, we will come to this, right, where does the epsilon come from, where does the delta come from. In some cases you also have that the delta is depending on the initial condition, and in this case it is not depending on the initial condition. So, it is usually called as the also referred to as the concept of uniform stability. Okay. So, we will drop this t naught for the moment and we will say, well, we are just dealing with uniform stability. Okay. A slightly milder version of this to give you an intuition of what this statement means, or a little understanding. X star is stable if for all initial conditions, for all initial times, the map t from x t, right, which is given by this solution. This is my solution, is a bounded map for all times t greater than or maybe even equal to t 0. Essentially, it means that phi or this solution x of t, okay. So, it is a bounded map. So, means the values of x never go unbounded. So, if I were to just draw a little picture, well, this could be solutions whatever and so on, right. So, these are all bounded. Okay. Now, what does this actually mean? Okay. So, let us see a pictorial version of it. Okay. So, I start, okay, with x star as my equilibrium point here. Let this x naught come from a delta ball. Essentially, a delta ball would be a ball centered at the equilibrium and of radius delta, and take any initial condition. So, I have this delta ball and take any initial condition within this delta ball, this x naught. So, the solution will, so if I just see this dotted line, the way it goes, it is always confined to this epsilon ball of radius. This is epsilon ball is again the ball centered at x star and of radius epsilon. Okay. So, if I just move this picture 90 degrees, it will look something like this. Okay, I will try to draw it as neatly as possible. Say somewhere I will just use this red color for the delta ball. So, this is my delta ball, and okay, I will come back to blue. So, what does this mean of okay, I start at some initial condition here, and as time goes by I am just within the solution is just within this cylinder. It could be go here and so on, but it will never breach this cylinder, right. So, it will just move along the cylinder. So, here I am actually even adding the time axis. So, if I tilt it, so these solutions will just move along this cylinder which is in this represented in green. Okay. So, essentially it means that the solutions do not go like unbounded. So, for example, if just say I started initial condition here and it just keeps going this way, this is an unbounded solution, and this is an unstable behavior, right. So, this is a very basic, very weak notion of stability, that this could just be doing whatever the solutions could just be doing whatever they want. One simple example is the linear oscillator that we did, right. So, it just keeps on oscillating, this is always stable, right. Okay. So, that is what this says, right. So, whenever the initial conditions are in a delta ball, the solutions will be confined to an epsilon ball, or that the solution or this map T to the solution space is always a bounded map, right. That is what is a very loose or the basic definition of stability. What is unstable? There is only one definition. Whatever is not stable is unstable. So that's the only definition of instability. You don't really check, oh, are the solution going to infinity, are they doing whatever, and so on. So whatever is not stable is unstable. Okay, so that's the only definition of a system being unstable. Okay, so just to give you a little very basic, seemingly trivial illustration of what is happening in this picture. So let's start with this second order system. X1 dot is minus x2, x2 dot is x1, and so on. Show that the equilibrium is stable. Right? So easy to verify that 0 comma 0 is an equilibrium. Okay, let's first compute the solution, right? And just let's for simplicity assume that the initial time is 0. So let x naught be the initial condition. Then the state transition matrix, well, we know how it is computed this way. I'll not go into the steps of this, but by now we know how to compute the state transition matrix. So given any initial condition x naught, which is a 2-dimensional vector x1 naught or x2 naught, the solution will look something like this. Okay. Now given x star, which is just the origin, what I would want to evaluate is checked for these two inequalities, right? If the initial condition is within a delta ball, are the solutions within an epsilon ball, or are the solutions always bounded? Okay, so let me compute this norm, right? So this could be a 2 norm or infinity norm or whatever, because we know that all norms in finite dimensionals are equivalent. So give me one norm, I can always find a nice relation with the other, or I can always bound it with the other norm. So it doesn't really matter which norm you choose, but for our purposes we will usually look at the 2 norm. Okay, so this, well, x star is 0, so this turns out to be just x naught. Okay, now the solution phi t x naught minus x star. So this is computations become easy, right? So if I evaluate the 2 norm of this solution, okay, it again turns out to be x naught. So what does it mean is that well, the initial conditions, so the delta, so this I found a bound to be x naught, or actually I found it actually to be equal to x naught. This is also x naught. Okay, so let's take a trick to verify or to understand what this means. What we know is the phase space. The phase space of these systems are concentric circles. Okay, so let me say I take this initial condition x naught. So this will be my delta ball. Okay, now where will the solutions move? Well, the solutions will move along this circle of radius delta, right, along all this. Now this is also equal to epsilon. That's what I mean when I draw these two pictures, right? I start with the initial condition at this point. So this is whatever is my initial condition. Then the final conditions will also be, or the solutions will just be circling around this again of the same radius. Further, if I say, okay, what if my initial condition is here? So I'll have a new delta. Let me call this delta prime, and my solutions starting from here with some initial condition will just be circling around here. Okay, so they never go unbounded, right? So that's the idea here. So I can just say take a larger ball like this, start from an initial condition here, and they will actually, the solutions will just be inside this. Okay, so very nice and a trivial example, but it gives us a nice understanding of stability. It's easy to check that this system will have complex eigenvalues and so on. As a exercise to check if the system is, or an example for instability, just check for this matrix and then try to compute the epsilon and delta values, and you will find that this will not exist. So you will not be able to bound this by some number from the above. Okay, so I will not really do that verge example of instability, because that it should be easy to check. And this is like what I proved here is I can just check that for every delta greater than blah blah blah, which is x naught, there exists an epsilon which is x naught, and hence the system satisfies the definition of stability. Right. Now what next? I really do not want systems which are, I really do not know where they are going, but they are just bounded. I want something stronger, right. So stability, I would rather want my system to come back to its equilibrium or its steady state position when it is subject to an initial condition, or there is a slight perturbation in the system. Now how do we mathematically define that notion? And that notion is the notion of asymptotic stability. So the definition states the following. So we will first read the statement and then try to interpret that. The equilibrium, again x star of this system is stable if, again, so all this epsilon delta exist as they would for, so the basic definition of stability should be satisfied. Now additionally, on top of that, an equilibrium x star is asymptotically stable, two conditions. One, if it is stable, and second, as t goes to infinity, x of t should tend to x star, which could be the equilibrium in this case for all initial conditions, right. So okay, let us see what is new here. First is so it means that as t, so suppose I am here, so this is my equilibrium. I say, well, I start from any point, I should actually eventually come back to this point. I can come back this way, I can come back this way, depending on the nature of the equilibrium point. Okay. So this is what it means. Now why do I superimpose a statement saying that stability is also a necessary condition? Why is it not always obvious that at t equal to infinity I am going to the origin? So why should I additionally on top of that check for stability? Okay, let's do an example of that. In the linear case, it might like be obvious, but there might be some classes of systems which would behave very strange. Okay, so let's do an example of this. Okay, so I have this system x dot equal to x square, and let me say that x at 0 is 1, right. Now what is the solution to this? The solution turns out that x of t is 1 over 1 minus t. Okay, so some strange thing is likely to happen. So at t equal to 1, my system will say start at say x 0 is 1, it will just blow up, right. So the value is not defined for t equal to 1, and you might think that, well, it will actually come back after t equal to 1 plus, and eventually if I apply the limit rule, what happens as t goes to infinity, this might actually come back to 0. I just draw it slightly better, right. Okay. Now is this a stable behavior? Well, this is not, right, because the solutions actually go unbounded. So what was the definition of stability? That whatever the solutions do, they should just be bounded by above by some number. Okay. This typically could happen in some nonlinear systems, and this phenomena where at t equal to 1 the system blows up is called the finite escape time. Okay, a phenomena not usually or almost never seen in the case of linear systems, and therefore to have a general notion of stability, we may have to impose this extra condition that first I need to check for stability, and then I need to check what happens to the solutions as time progresses, what happens asymptotically to the system. Okay, so what does that mean? Pictorically, I think this should now be like kind of easy to visualize now, right. So if I go back to drawing the cylinder diagram, start from any initial condition, I think that is a nice way to look at it is, okay, it just comes back to the equilibrium position. This is the equilibrium or x star. Okay, this is with time. Okay, so similarly here I start with here, and somehow I just say, well, so this is at t equal to, as t goes to infinity, I come back to x star. Okay, so that is this is a stronger condition to check, right. So for example, is this system asymptotically stable? Well, the answer is no. The system is not asymptotically stable. Is it stable? Yes. So first thing, okay, which is a larger set? The earlier system was stable, but not asymptotically stable. So asymptotically stable is bigger, is a restriction on it, right? So this will be asymptotically the set of asymptotically stable systems. It's a stronger condition. So not all asymptotically stable systems are stable systems, but not all stable systems are asymptotically stable systems. So it's like if I were just to say asymptotic stable and stable, all asymptotic stable systems are stable, but all stable are not asymptotically stable systems. Okay, just a little counter example to that is what we saw just now. Okay, so let's do again seemingly simple looking example. If I just were to ask you to compute the state transition matrix, the solution, it will just be like by heart, right, because it's in the diagonal form, and then the e power at is easy to compute. Let us say I start with certain initial condition x1 naught, x2 naught. Again, for simplicity I assume t naught is 0. First, can I check for stability? That will be easy to check, right. So this is my the delta ball. This will be how the epsilon ball would look like. So the first two conditions will tell me that the system is stable. Okay, now how do the so I can actually find the upper limit of this, right. So I'll just leave that as an exercise. But what look at this this expression here. What happens? It has two terms which are exponentially decaying, right, and therefore yeah, if I put the limit as t goes to infinity, I'll just end up here, right. So limit t tends to infinity, phi t naught x naught is the origin, which is the equilibrium of interest. Again, simple example, but good enough to verify what is happening here. Okay, is that, are we happy when we say this? Okay, this is just a statement which concludes that the system is first, that this system is stable, okay, and second, that this system is also asymptotically stable, right. So just repeating that and writing down that formally. Okay, so are we happy with this? Well, one may ask, how fast are we coming to the origin, or how fast are we converging to the equilibrium point? So whenever I say origin, it also means the equilibrium point. So these things will be used interchangeably, origin, the equilibrium, and so on. So I would also want my system, say for example, it takes forever, right. If it's a very heavily damped system, maybe the response is very slow. And therefore, I would also like to see what is the rate of convergence to the equilibrium point. And therefore, I need to define further a stronger notion, or can I quantify the rate of convergence, and that is where comes in the notion of exponential stability. Okay, what does it mean? Again, the basic thing is to look at the definition of stability. Okay, when is the system additionally exponentially stable? Of course, first I should check if it is stable or not, and then there exist two constants, alpha and lambda, such that something like this holds. Okay, what does this mean? Say suppose I have a solution which starts from initial condition, it goes whatever like this, and maybe eventually goes to the origin. Now exponential stability would mean, can I actually bound this from above by an exponentially decaying curve, right. So this is exponential decay, right. So if my solutions are always under an exponential curve, then this is called an exponentially stable system. Mathematically, well, this is an exponential, my solutions, so this is my solution is bounded by an exponential function, right. This is exactly what is written here, right. So this will be called the decay rate and so on, right. Okay, so I can just write down a picture which looks like this, but I think it's easier starting from what we know earlier. It is now easy to interpret this picture. Okay, again I come back to this system. Now I want to verify if this is exponentially stable, and then if it is exponentially stable, what could be the values of this alpha and lambda. Okay, I'll again skip the initial condition, skip the little computations. Again t naught could just be the t naught equal to 0. Okay, so again this is from previous. So what does the solution satisfy? Phi t x naught minus x star is just bounded by e power minus t. So it decays at a rate of lambda equal to 1. Okay, so this 3 steps can be easily verified. I am just computing the 2 norms here, so that should be easy. Now so far, well, we know that this is stable. Something inside could be asymptotically stable, it is a smaller subset, and exponential stable is even a harder condition to check, right. So therefore this is the strongest condition to check would be that of exponential stability. So stable is just is a bigger set. Asymptotically stable systems are stable, exponentially stable systems are asymptotically. So now a relation between asymptotically stable and exponentially stable. All exponential stable systems are asymptotically stable, but are all asymptotically stable systems exponentially stable? Well, it turns out in the LTI case, which means the linear time invariant case, exponential stability and asymptotic stability would actually like coincide, right. And we will do proofs of this. So I just conclude today by just introducing to you the 3 notions of stability, the basic definition of stability, asymptotic stability, which is a stronger version, and something which also tells us the rate of convergence is the is exponential stability. Now given a system, now how would I verify stability? Say I am given system in R4. Now can I all the time compute the solutions, compute those constants alpha, lambda and so on, or compute various norms? That may not always be easy. Now are there effective computational tools which will help us verify stability of systems? Similarly in the transfer function case, we do not really compute the check if the impulse response is absolutely integrable or not, right. We just translate that to an easier way of verifying, which is with respect to the poles. Similarly in the state space methods, we will next look at the notion of Lyapunov stability and identify tools which will help us verify stability certificates for LTI systems. Again, much of the tools that we will use will come from week 2 and week 3 lectures of linear algebra, and of course a part of week 4 and week 5. So that will be coming up in the next lecture. Thanks for watching.